Fundamentals of Bioreology and Hemodynamics. Hemodynamics we consider as part of biomechanics, where we study the motion of blood through our vascular system. So the central physical characteristics for hemodynamics is pressure, which we define as action of blood per unit area of the vessel wall, and use this formula for its definition. Another main indicators of hemodynamics is linear velocity, which is the distance covered by the blood particles per unit time, and the volumetric velocity, which represent the rate of volume change or volume of our fluid that flows through cross-section of the vessel per unit time. Linear velocity of blood in aorta is estimated to be about 0.4–0.5 meter per second, and in the capillaries it is about 1.5 millimeters per second. We have such a relationship between linear and volumetric velocity, so these characteristics are closely related. Then the motion of jet continuity is of great significance when we consider hemodynamics. If the fluid field and velocity field do not change with time, then the motion of our fluid we call stationary. For stationary fluid, the mass of liquid flowing through considered section of the vessel per unit time remains constant. So if we choose such a vessel like we have in this picture and choose the cross-section 1 and cross-section 2, we can write such relation between linear velocity, volumetric velocity, and cross-sectional area for this part of the vessel. So we come to such formula which we call the equation of continuity. This formula gives us information that the less cross-sectional area we consider, the faster motion of liquid we get. If we consider the change in the total energy of system, we know that it can be caused by the work of external fields. Of course, if we do not take into consideration the shear forces inside the system. So the usual definition of mechanical work we consider as product of force and displacement. If we choose a blood vessel with cross-sectional area S1 and S2, as we have this here in the picture, the work represent such difference, where a product of P1S1 and P2S2 represent the force acting in this part and in this part of the vessel. Total energy we consider as usual as sum of kinetic and potential energy. So from one side we have work of external forces, and from another we have change of internal energy, which we represent as difference between kinetic and potential energy in final state and kinetic and potential energy in initial state. If we gather in all quantities with the same indexes together and divided our expression by volume, we obtain such expression where ρgh represent hydrostatical pressure, ρv squared divided by 2 dynamical pressure, and P is static pressure. This equation we call Bernoulli's equation, and it is represented the conservation law of energy for unit volume of moving liquid. When we consider the relative motion of layers of liquid, we come to notion of internal friction forces, which can be described according to Newton formula. In this formula, eta is dynamic coefficient of viscosity, dV per dx represent the velocity gradient as surface area of the layers, and dynamic coefficient of viscosity we define as friction force which acts on unit of conduction area of the layers when the velocity gradient is unit 2. The units of measurement for dynamic coefficient of viscosity is Pascal per second. The velocity gradient represents the direction of increasing the rate of change of velocity. So when we consider the motion of the blood through the vessel, the maximum velocity we have in the center and the minimal velocity we have along the vessel walls. No systematic unit of viscosity is poise, which is 1/10 of Pascal per second. Of course, considering the dynamic coefficient of viscosity, we can make some conclusion about the healthy state of patient. So, in normal state, the dynamic coefficient of viscosity is 0.004, 0.005 Pascal per second. Very often it is convenient to use relative viscosity of coefficient, which we define as the ratio of viscosity coefficient of solution to the viscosity coefficient of a solvent. As all our liquids in our organs and tissue represent the water solutions, so our solvent we consider the water. Normal value for relative viscosity coefficient is from 4 to 6. Relative viscosity coefficient is dimensionless value. Kinematic viscosity coefficient we consider as ratio of dynamic coefficient of viscosity and density. When we consider motion of liquid in vascular system, it is natural to try and to construct models for describing their behavior. So the simplest model of liquid is an ideal or perfect fluid that is not subject to compression, so the pressure remains constant, and in which there are no friction force. So our dynamic coefficient of viscosity equals to 0. For Newtonian liquids, the viscosity coefficient depends on the temperature and nature of the liquids without dependence on the flow conditions. Examples of Newtonian liquids we can consider, for example, water, electrolyte solution, mercury, alcohol, etc. Liquids where the viscosity coefficient depends on the condition of the flow, we call non-Newtonian ones. And example of such liquids proteins, polymers, suspensions, and blood, of course, is non-Newtonian liquid. And this is due to the fact that blood has an internal structure, plasma, as almost Newtonian liquid and formed element of the blood, because 93% represent the electrocytes. So blood can be considered as suspension of erythrocytes in serum, and its viscosity varies along the bloodstream depending on the flow condition. When we consider the peculiarities of fluid flow, we come to notions of laminar and turbulent fluid flow. So, the laminar flow of liquid is that where each particle of fluid moves along smooth trajectories that do not intersect. Turbulent flow is the flow which hydrodynamic characteristics such as velocity, pressure change sharply and irregularly with time and in space. To estimate the probability of turning of laminar to turbulent mode of motion and vice versa, we use such parameters as Reynolds number, which can be defined according to this formula. And here we have V, average linear velocity of liquid, rho density, and D, internal diameter of vessel. We have for each given fluid a certain critical value of the Reynolds number. For example, the Reynolds number for the water equal to 2,300. Critical value for Reynolds number for the blood is 2,000. If our Reynolds number is greater than critical value of Reynolds number, then the motion of liquid in the vessel is likely to be turbulent. And in other case, we can consider it as laminar. Blood is a viscous fluid that during the motion through the vessel causes shear stress on the wall of the blood vessel. During the flow of the blood, there is a force which is directed along the vessel wall and under direction of which the inner surface of the vessel, I mean the layer of endothelial cells, must move with the flow of the blood. In the case of laminar flow, the shear stress of the vessel walls is directly proportional to the velocity of the fluid. The shear stress is determined by this formula. Shear stress is a very important factor in pathological conditions. For example, atherosclerosis plaques tend to form when large vessels divide into smaller ones. This place is due to a series of hemodynamics reasons. Have a significant shear modulus. And when blood flows through a narrow opening of the vessel under pressure, the laminar blood flow changes to turbulent. When we consider the shear stresses, a very important characteristic is elasticity of the vessel, which we can determine by this formula. Here, delta V represents change in blood volume, delta P represents transmural pressure, or the difference between internal and external pressure on the vessel wall. Here in this picture, you can see the mechanism of formation of deposits in the places of branching of our vessel and formation of cholesterol deposits or, for example, blood clot. Here in this picture, you can see the difference between clear artery and artery with atherosclerotic plaques. So this can represent how the linear velocity can be changed when our internal diameter shrinked and we have narrowing of the vessel. So we have striking of the blood into the wall of the vessel, to be exact, to these deposits of atherosclerotic plaques, and we have fastening of our blood motion and rising of force of vortices. Then the main equation of hemodynamics we called Poiseuille formula, and this formula relates volumetric velocity with gradient of pressure, with geometrical parameters of our vessel, and viscosity coefficient. If we denote the ratio of H at L divided by pi r to the fourth degree Sx as vascular resistance, then we obtain Huygens-Poiseuille formula, and so we can get a lot of information starting from this formula. So we can see that volumetric velocity is directly proportional to the pressure gradient and inverse proportional to the vascular resistance. Considering the formula for vascular resistance, we can say that when the blood flow through the vessel, there is resistance to the internal friction between the layers of fluid between the blood plasma and the walls of the vessel. Hydraulic resistance of the vessel depends mostly on the radius of vessel, and the value of volumetric blood flow depends on the numerical value of resistance. So the highest resistance we have in the smallest vessels in capillaries, and the lowest resistance we have in aorta. The largest pressure gradient we have in aorta, and the lowest pressure gradient we have in capillaries. When we consider branching of our vessel, we can use Kirchhoff rules to find the total resistance, total pressure gradient, and total volumetric velocity in case of a series and parallel connection of our vessel. So, if our vessels with resistance x1, x2, xn connected in series, then the total resistance we can find as sum of all resistance for each part of such a system. The same we have for pressure gradient. Total pressure gradient represents the sum of pressure gradient in each part. But volumetric velocity, according to the equation of jet continuity in such system, remains constant. When our vessels connected in parallel, when we have such branching of our vessel into smaller ones, we have formula for resistance of parallel connection. The inverse total resistance represents the sum of inverse resistance of each such branch. Volumetric velocity equal to the sum of volumetric velocity in each parallel branch, but total gradient of pressure remains constant. Pulse wave represent the processes of propagating the change in blood volume along elastic vessel as a result of simultaneous change in blood pressure and mass. The origin of such waves is related to the reaction of elastic walls of the vessel to the pulsating flow of the blood, which occurs during the periodic walk of our heart. So, when we consider the propagation of pulse wave along our vessels, we can describe it by such exponential law. Pulse wave amplitude or pulse pressure P0 represent the difference between maximum and minimum numerical value of pressure at this point of vessel. Beta represent the damp coefficient, which increases with decreasing of radius of our vessel. The speed of propagation of pulse wave along the vessels depends on properties on the blood and blood vessels, and we call to this formula for velocity the Molen-Skorteweg formula. So here we have square root of ratio vessel wall thickness H, Young modulus E, and in denominator we have density of the blood and internal diameter of our vessel. The speed of pulse wave, which we estimated according to this formula, is 6 to 10 meters per second, and this many times faster than speed of blood flow in our arterial system. If we take the systolic period, the period of contraction of our heart, which is estimated to be 0.3 seconds, the pulse wave propagates by 2 meters for this time. When we consider the pressure in our vascular system, then we should say that more than 95% of heart work is due to the potential energy of compressed fluid in aorta, which in its own turn is determined by the value of average blood pressure. Average blood pressure can be determined by this formula, where we have diastolic pressure, which is the minimal pressure in aorta, difference of systolic and diastolic pressure. Systolic is maximum pressure in our aorta divided by 3. Normal values for average pressure is 90, 100 millimeters hydrarchal. This difference of systolic and diastolic pressure, which we call the pulse blood pressure, tends to increase with age, and this fact is due to decrease in elasticity of arterial walls. Another very important blood pressure indicators we call the minute blood volume, which is the volume of blood which flows through each part of vascular bed in 1 minute. So through the aorta, pulmonary artery, through the total cross-section at any level, the same amount of blood minute volume flows. At rest, minute blood volume is about 5 liters per minute. But under intense physical load, after intense physical exercises, minute blood volume can be increased more than 20 liters per minute. If we consider the work and power of the heart, quite a lot of energy is needed to dilate the walls of aorta during systole and the motion of blood through our vessel. So if we consider the work of the heart, consisting of work of right and left ventricles, we get such a sum for definition of heart work. The work of the left ventricle, which throws blood into the great circle of blood circulation, is greater than the work of right ventricles. And here we have such relation between work of the right ventricle and left ventricle. So the total work of the heart is estimated to be 1.2 work of left ventricle. The work of the left ventricle of the heart is used to overcome the forces of pressure in vascular system and providing our blood with kinetic energy. The force which acts on the blood in the ventricles of the heart depends on pressure and inner surface S. So we have such usual formula. According to Stalin's law, the force that occurs during heart contraction is proportional to the initial length of the myocardium. So we can substitute the definition of force as product of pressure and surface area, and product of surface area and the length of myocardium give us volume. So to get the kinetic energy, the volume of the blood should do such work. A2 equal mv squared divided by 2, or that is the same rho v squared divided by 2. So the work of left ventricle we can represent in such form, and a work of the heart equal 1.2 times this expression in our parentheses. Then, if we take the pressure in the aorta is 13 kilopascal, blood volume is 60 milliliters, blood density is 1050 kilograms per meter squared, blood velocity is 0.5 meter per second. Then estimated work of the heart for one cardiac cycle is about 1 joule. If we calculate appropriate power of the heart per 1 systole, then we obtain value 3.3 watts. On average, the heart performs 1 contraction per 1 second. Then we can calculate the work of the heart per full day, and this work is 86,400 joules. In human body, we have about 160 billion capillaries with total length of 100,000 kilometers. And for the whole life of human, 1,050 to I apologize, 150 to 200,000 tons of blood pass through the heart. Then, to determine the blood flow velocity, we can use two methods at least. The main methods is ultrasonic methods based on Doppler effect. For these methods, we have from the ultrasonic oscillation generator, the signal enter the ultrasonic emitter, as you can see in this picture, and frequency comparison device. Then it penetrates the blood vessel and is reflected by mobile erythrocytes. Then a reflected wave enters the receiver. The comparison device compares the incident and reflected signals and determines the Doppler shift. For Doppler frequency, we have such formula where V is ultrasonic wave velocity, V0 our erythrocyte velocity, or which is the same our blood flow velocity, nu as source frequency of ultrasound, and nu d Doppler shift frequency. In large vessels, the speed of erythrocytes varies depending on their location relative to the axis of the vessel. Ultrasound waves are reflected from erythrocytes, so Doppler shifts are obtained not in the form of only one frequency, but as a frequency range. Another methods we called for determining of blood velocity, we call the electromagnetic methods. The main features of this method. When we have moving charge in magnetic field, the Lorentz force which acts on this charge, we can describe using this formula. Under action of Lorentz force, There is the distribution of charged blood particles near one wall of the vessel. For example, we have the particles of one side, and near the another wall we have particles of opposite side. Such distribution of charges along the cross section of the vessel leads to the appearance of electric field. This physical phenomenon we call the Hall effect. If we measure the potential difference between walls of the vessel, we can find the linear velocity of the blood flow and volumetric blood flow velocity according to this formula. That is all. Thank you for your attention.